This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2018 AP Calculus exam, Free Response Question AB2. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on or highlight the solutions presented in these guidelines, not how the points were awarded. This question was calculator active, so I'll show you how to use technology to explore and answer parts of this question and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. This problem involved the particle moving along the x-axis with velocity given by v of t. And we also know the initial position of the particle. In part A, we need to find the acceleration of the particle at time t equal 3. In part B, we need to find the position of the particle at time t equal 3. In part C, we need to evaluate two slightly different definite integrals and interpret each in the context of the problem. And in part D, a second particle is added to the problem, with position function given by x sub 2 of t. And we need to find the time at which the two particles have the same velocity. Part A was worth 1 point, simply for the answer. We need to find v prime of 3, and we should do so using technology. Part B was worth 3 points. Using the fundamental theorem of calculus, or the net change theorem, 1 point for writing the definite integral from 0 to 3 of v of t dt, 1 point for using the initial condition on the way to finding the position of the particle, and 1 point for the final answer, the position of the particle at time t equal 3. Part C was worth 3 points. 1 point for the two answers, the two definite integral evaluations, and 2 points for the correct interpretations of each definite integral in the context of the problem. Part D was worth 2 points. 1 point for setting the two velocity functions equal, and 1 point for solving this equation to find the time at which the two particles have the same velocity. In Part A, once we recognize that the acceleration is the derivative of the velocity, this problem is pretty straightforward using technology. Using the TI-Nspire, I defined the function v, and then simply found the derivative of v evaluated at t equal 3. And just because I'm using a CAS machine, I wanted to see if I could find the exact symbolic derivative. I had to define v a little differently here, using exact values, no decimal approximations. And here's the exact derivative at t equal 3. Note that some students actually found a derivative by hand here and substituted t equal 3. Although longer and susceptible to more errors, this is a valid solution. In Part B, we need to find the position of the particle at time t equal 3. I solved this problem by using the fundamental theorem of calculus and solving for x of 3. Some characterize this as the net change theorem. Now, we're given the initial condition of position, x of 0 is equal to minus 5, and I can find the value of the definite integral using technology. The final answer here is minus 1.76. Now, remember, I already defined the function v on a previous calculator page. Even though I could find the position of the particle in one step, I like to solve these problems in pieces. Here's the value of the definite integral, and here's that value minus 5. The position of the particle at time t = 3 is minus 1.76. Here's an example using some of the information given in this free response question. Suppose the particle moves along the x-axis with velocity given by the same function v, but now on the time interval 0 to 7. And let's assume the particle is still at position x = minus 5 at time t = 0. First, sketch the graph of the position function of the particle, and then find the time t when the particle is farthest to the right. Oh, and find its position at that time also. I'm going to use technology to solve part A and leave part B for you. I first define the position function s, and note the use of the variable t and the dummy variable x here. And I thought it would be nice to see a graph of the position function and the velocity function on the same coordinate axes. And another question now comes to mind. Explain the relationship between these two graphs. Now, you can certainly use these graphs to explore the answer to part B, but I think you should consider solving this problem analytically, well, as much as possible until you need to use technology. I think there's some good calculus here. In part C, to begin, all we have to do is evaluate the two definite integrals. And that's pretty easy using technology. The value of the first integral is 2.844. And this is the change in position of the particle, or displacement. Note that another way I could get this is the difference in positions at t = 3.5 and t = 0. Using my function s defined previously, that's just s of 3.5 minus s of 0. The value of the second integral is 3.737, and this is the total distance traveled by the particle over the time interval 0 to 3.5. Here are some graphs to confirm and visualize these results. I graphed both v and the absolute value of v on the same coordinate axes. Here, the value of the first integral is the area of this shaded region minus the area of this shaded region, 2.844. The particle moves to the right for a while and then back to the left. The accumulation of the velocity function is the net change in position or displacement. The graph of the absolute value of v is the same as the graph of v where v is positive, and reflected across the x-axis where v is negative. The value of the second integral is the area of the shaded regions. The accumulation of the absolute value of velocity is total distance traveled. In part D, we simply need to set the two velocity functions equal and solve for t. The velocity function for the second particle is pretty straightforward, 2t minus 1. But we need technology to solve for t. Here, I defined the position function for particle 2, and I used the solve command to find the value of t where the two particles have the same velocity. And here's a graph to visualize and confirm this result. I graphed both velocity functions on the same coordinate axes, and then I used the Analyze Graph menu to find the point of intersection on the two graphs. Here's one more AP Calculus type question that uses some of the information given in the free response question. Suppose particle 1 moves along the x-axis with velocity given by v sub 1. This is the velocity function given in the free response question. But let's consider a different time interval, 0 to 7. And we'll use the same initial condition for particle 1, x of 0 is equal to minus 5. Now, particle 2 also moves along the x-axis with velocity given by v sub 2 for t between 0 and 7, with initial condition x of 0 equals minus 1. Now, let's assume that if the particles are at the same position at the same time, they won't collide. They just pass freely by one another. First, find the position of particle 2 at time t equals 5. Then, find the total distance traveled for particle 2 over the time interval 0 to 7. In part C, find the times when the two particles are traveling in the same direction. In D, find the time when the two particles are farthest apart. Find the times when the particles are at the same position and determine whether the particles are moving in the same direction or opposite directions. And finally, find the limit as t goes to infinity of v of t and explain this result in the context of the problem. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions and of how to use technology to solve some of the parts of this problem and to explore, confirm, and visualize results. This problem presents some good opportunities to discuss and really understand the difference between displacement and total distance traveled. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.